Hi everyone, welcome back to the LLM Bootcamp Zero to Hero in LLMs. Today we'll be starting off with week 5. That is, we have module 9 and module 10. Module 9 is nothing but transfer learning and multimodal models, where we'll be working on generating image captions for the input images using multimodals. We have vision transformers, and then we have OpenAI clip models which are already built, and we have lots of research paper which is written on this particular topic. And we have Armielyn Obinguar, who is a CTO at Safe and previously has also worked at Accenture as MLE senior, and is also part of AWS community builder. So without further ado, let's start with the session and learn more about multimodals. Over to you.
All right, thank you so much. Okay, let me try to share my screen. Yeah, okay. So I think we can start maybe just giving you a highlight of what would be sharing for this. So basically, we're focusing on the generating caption images using multimodal fusion in NLP. So I'm Armelin, and I'm here to actually share more about it. So basically, you can actually scan this QR code if you wanted to connect with me as well on my LinkedIn and
Actually,
other.
the slides are not visible.
Okay, sure. Let me try
Yeah,
to.
now it's visible. Okay.
Okay. All right. Yeah. Can you see it?
Yeah, it's visible now.
All right. Okay. See. Okay. All right. So yeah, again. So I'm here to actually share more about
Okay,
generating
so
caption images
basically,
using.
when you click on the next slide, it is showing click to the exit full screen.
Oh. Okay.
Yeah, now the QR code is visible. You
All
exited.
right. Okay. Yeah. This one. Can you see it?
Yeah, it's showing loading, and then click to exit full screen.
How about now? Can you see it now?
It's showing click to full screen. So can you reload once? Yeah,
Okay. Sure.
or
Let
else
me
you
try.
can view it like this itself. We are able to. Okay. So yeah, she'll be joining back due to few technical issues, and until she comes back, I want to give few updates. Like module 9 and module 10 are already. Module 9 is live on the website. You can go and check out the notebooks and start practicing. Okay, so we are back.
Okay. Sure. Yeah. Thank you so much. Apologies. Let me try to share my screen again. Okay. How about this one?
Yeah, it's visible. Can you click on slideshow?
All right. Okay.
Okay, so I guess slideshow is not working. So we can just maximize the slides and you can walk through the slides.
All right. Okay. Thanks. Thanks a lot. Okay. Can you see it now?
Yeah, the slides are visible.
All right. Okay. I can start it. Okay. So, yeah, thank you so much. Apologies for any technical issue. So, we will be discussing more about generating caption images using multimodal fusion in NLP. So, this is for the week 5. Yeah. So, if you join a lot of previous sessions, so maybe you have like a brief familiarity of some of the concepts. So here again, me, Armielyn Obinguar. So if you wanted to connect with me or probably you know be connected as well on my social, you can always scan this QR code. But I will just show this later on as well. All right. So of course, before we start off my a little bit discussion, probably some of you have familiarity with Pokemon or have seen this online or maybe like a fan of it or using. Maybe you can chat on the YouTube live if you are pretty interested in Pokemon and so on. So basically, based on these pictures, it's actually what you've noticed here is that there's actually a caption. So a little bit, info about this is that, some of the time, whenever we use actually images or trying to generate caption itself, sometimes it gets more a little bit, harder before. But now that we have pre-trained models that we're using Hugging Face and coming from the vision transformers, we can actually generate something like this. So basically, if you notice some of this, maybe we can look at one Pokemon here, it generates like a blue and a green bird with a yellow tail. So this is one description. It basically look at the color and then in general. So just going further with some of the images, garden of a crescent moon with a pink eye. So it's another one type. As you can see, it really somehow it tells about the descriptions of this. And then the third would be a drawing of a woman standing on the top of rock. Well, it makes sense because this one, standing, of course, on the rock. And going to next, it's just a drawing of a pink bird flying through the air. So basically, all these stuff right here, it generates, image to text, especially for that. And then, as you can see, other images as well here, it just describes, overall the features basically from that sense. And it relates to actually about, this concept of natural language. So as you can see, when you think about this, it's just an image. So how does these, models or transformers were able to generate the text? So basically, it just learns actually the language that we know, the human language, which is English and other languages, of course. And then from there, it tries to, look at some of the features that are really, relevant to generating the captions. So starting off, maybe we can focus on this one. So what do you think, how do you think this certain um caption was generated? Any idea? Like before it is generated into like a captions, is there any, thing in mind like how this thing really works? Does the machine already know how to do this, or is there any other mechanism that these certain one? So perhaps you can always chat here, but yeah, so from here, the certain picture here, it's all about the drawing of a small animal with a pink nose. So going to this, the machine learning or the vision transformer itself will just actually convert this into numerical representation. Where in fact that some of these parts or all these parts right here, it's just the numbers. So it tries to find which one of these parts would be relevant for the captions to be generated. So as you can see, what it really sees is that those numbers, okay? But the output seems like this one, right? So whenever you think about these image captions, it doesn't just really a magic or something that pops it somewhere, but basically starts off with how to actually now extract features. So perhaps maybe I show you this one. Um, this one is more about how the words get relatively categorize. So this is actually relevant in the sense of
Uh,
creating
hi, hi.
captions.
Sorry for the disturbance. Hello. So there is little bit of disturbance in the voice.
Yeah, can you hear me now?
Are there any two mics which are operating? So there is little bit of vibration noise.
Okay, let me try to check my mic. Can you hear me now? Is it clear?
Yeah, now it's clear.
All right. Okay. Thank you so much. Okay. All right. So let me go back again. So sorry about that stuff. Okay. So again, we have here this image. So just describing here, we have this caption. So one question we have to think about here is that how does it generates? So by looking at this, at some parts of it, creating a bounding boxes, and from here it converts into a numerical representation. So now we can see those numbers right here in the bill and the other side. And now the one question here is that how does it extract those information? So from here we just simply, find some relevant part here, and then from there it could contribute to the possible output, which is the caption itself. And now going to here, this is also related to generative AI as well, is that these words actually relates to how does it categorize. So for example, here we have this word embeddings. So you basically first try to just categorize words. If it's from dog and cat and the other side car bus. So we just categorize it in just other area and the other one. And then one thing that we notice from here is when we try to add a little bit more words. So whenever we add some words here, is that it tries to actually now look at other side. Maybe the drive comes in different, not part of the dog walk or the vehicles. It came from the other side. So now we can relate to generating captions. We have to actually look at how these model could actually generate those words, and then of course that's how the language models definitely comes in. And a lot of it, the word Tvec, it's another one that we could also use for this. And it summarizes to the natural language processing, wherein we can summarize text, do question answering, sentiment analyses, or speech language understanding. So perhaps let's have this a little bit, before we go into the notebook, starting to discuss how does it work. So first here we have this, next word prediction with memory, such as recurrent neural networks. So this is RNN. And this sentence from here, I don't know if you guys are familiar with this. It's very popular in the sense that it does now ask the question what this sentence means, for example. Because whenever we look at images, we try to make sense that how does this words came out like, right? So from here, we basically look at is either a person or a rabbit, or maybe we could try to use now another methods to actually predict the words. So from here we get this one word lazy, and there's a lot of definitions we can think about lazy. It could be a person or probably another word. So now the question here is that how can we use those transformers or this what we call attention is all you need? A paper published in 2017, done by created by Google Brain and the researchers from there. They actually think about that, those transformer model architecture, we can actually enable this to scale the understanding of relationship between words and tries to mix, some predictive stuff around it. So we can actually relate the concept to what we're going to be showing you later on. So perhaps let me try to show you this notebook. So hopefully we could try to catch up on. So starting on, of course, the Pokemon. So I'm sure that some of you are pretty much familiar with this. So let me just try to run into this one. So I'm using the Google Colab. So it's pretty, I know some of you were able to use this a lot of times with your projects. So basically, we're trying to install the Transformer, library. So from here, we try to first see what data sets we were going to use. And since I gave you a hint about it, so we can start off using the Pokemon datasets. So first, image captioning is a task of predicting a caption for a given image. And then common for this would be for aiding visually impaired people that can help them navigate through different situations. And another thing here is that image captioning helps to improve content accessibility for people by describing images to them. So this isn't something just simply doing a caption and it's done, but relatively common to a lot of applications that we use in daily life. And then, of course, here we try to fine tune an image captioning model and then use the fine tune model for inference. So starting off, yeah, it's actually optional to install this, but if you wanted to give it a shot for this one, then definitely do this. So just adding more transformer data sets and then the zero. So we're gonna explain that later on. So of course, the next part here is logging in. So I'm just gonna copy paste my token here. So if you are opening, if you have account for Hugging Face, then it's definitely easy for you to start working on this. So that's one. It's successfully logged in our token, and then now we can start working on this. So basically, yeah, this is the Pokemon blip that I showed you a while ago for the presentation. So let's just run this, and specifically coming from the Transformer datasets. So let's try to load this one. Yeah. All right. So yeah, it's faster than I think so. All right. So let's just give it a moment. So hopefully everyone is still catching up. So if you have any questions, just ask me later on. So here we can see that you're using the Lambda Labs. So yeah, we can actually have now the number of rows, the image, and the text. So we're visibly gonna start now. So first, we have to explain why do we have this image and text on the dataset. So first, our goal here is to generate a text or a caption from that images. So many caption datasets contain multiple captions per image. In those cases, a common strategy is to randomly sample a caption among the available ones during training. So we can either do now the speed and test or the train and test as well. Do speed now for our training and of course for our test later on. So just trying to log in. So basically, I know some of you are familiar with this. So we're just gonna have our train data for training data sets. and coming from the test datasets as well. And of course, let's now try to just visualize our training dataset. So let's see how this, certain captions. So as you can see here, we have tried to just show some of the few, at least 5 of them, images. So we have here one, a red and white ball with an angry look on its face. Very pretty much accurate on that sense. And second here is drawing a very cute looking Pokemon. So I like how that it uses the very cute. Well, that's pretty nice, but it still needs more improvement because it doesn't define what color it is. It's just simply giving us this one. And another one, a cartoon character with a backpack on his back. It's probably pretty much okay. There's the bag there. And of course, another one here, an emote, 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 emote. What does it mean? So it's still in progress. We're trying to still generate more and more in training this data set. And the next here, a couple of accordant styled items on a white background. So, well, it makes sense. But again, we're trying to test this and trying it. So if there's an error to this, it's just pretty much okay. So let's try to show another more images. Okay, so let's try like 10 for, yeah. But basically this one is just really working generating as in images. So that's why you see on the presentation as well. So let's try to have just focus on another one images here. So this one here, it's a different set of images. So we have here a blue and green with birds. So it's the same. And another one is another images for captioning. So to prepare the data sets, we have used actually here this one. So since we have image and text, the processing the pipeline will pre-process the images and the caption. So we have to use the preprocessor before we go into modeling. This is something that we should take note about. And so that we can fine tune it. And then later on, we can basically have this part as well. So going further with that, it just simply, try to transform now and tokenize those captions so that we can have at least those words being put into the for this one. So basically, with the starting point here is just it's pretty much simple. You don't really think about more like okay, make things complicated whenever you do an image captioning, but it simply tells us that you can use different kinds of data sets. It's not like the Pokemon only, but make sure that you have those images in the caption so that you can train and test now the model. So another thing that I could also show, this is very interesting application as well. This one. So this is also from the TensorFlow. And another one here, the first notebook that I show you is actually from, Hugging Face. So going further here, it's also another type of, transformer that we could also use from here. So now this one is what we call the show attend and tell, the neural image caption generation with visual attention. And it has been used for, 2-layer transformer decoder so that we can get most of different kinds of, feature maps, attention maps, and so on. So I'm going to show you that later on. So this is one architecture for this. So basically, we will explain how this certain caption was generated. It's pretty much very defined in some ways. So this is one example that I could show you. So this certain image here, the one that, surfing, of course, as you can see, every images that here that you can see here, it has to look at the different bounding boxes. And same with the other one that I show you, that there's actually parts where there it looks into what significantly contributes a lot to the output. So for example, here we have that surfer is surfing on a wave. So first part, image here, look at some part of that, image, and then recognizes that it could be starting, yeah. Well, definitely it's interesting that this model can actually, have this knowledge on grammar and stuff, right? The second one here is that looking at to the surfer itself, the one that is, and then we can see those boxes, and then it highlights basically, and then is another one, and then look into the surfing, what they do, what does the person do with that image. So it's surfing. So now going to the next one on what it could be on a wave, right? It could be like on the board itself. So basically, those what we call the certain vision transformer could actually give us these importance of okay, each of these bounding boxes corresponds to what the words would always tell us. Going to next, actually, let's try to install this and start to show you actually how this works. So let's have this library set up. Okay. And then we have this, of course, yeah. Well, it's faster now because, all right. Okay. So let's now insert the data set. All right. Okay. All right. Okay. It's almost done. Yeah. All right. So we're just using the TensorFlow as well. So can you? So a while ago we just used the Hugging Face, the pre-trained model as well. But now we're trying to make use of another one. So we're just showing two different ways to actually do the image captioning. Right. So now let's go here. Okay. Another one. Yeah. Let's have it first installed before we encounter so many errors if it's not installed. So we're just gonna import some of the libraries. Okay. Yeah. So we have TensorFlow here, datasets, and the common ones that we also use on training models. And of course, this one is optional, but if you want to tokenize the text, of course, the captions, you can always do this one, and then tries to also do some feature extractor for those images that you have. So, and then let's start with this one. So of course, since a lot of data sets are available for this, we try to use the Flickr 8K. So it's very popular ones because it has this at least 5 captions that you can actually use. So let's start off just running this data set. Okay. Yeah. All right. So it's actually now done, and then we're just setting up the captions as well. So of course we have here the training and validation, as you can see. So we're good with the captions and then the images that we can use. So it's Flickr 8K. And then going forward, let's have it, download on our end. Okay. Yeah, we're just gonna wait. But if you have a questions, just chat it. Okay, so far we have this 10,000 and validation of 5,000. Not bad for generating captions. So it doesn't need to have like a more ones, but if you are starting to just create something like a project related to this, you can always, have this kind of number of data. All right. So of course, the loaders for both dataset have TF data, that datasets which contains the image path and caption. So similar to the previous one that I showed you for the Pokemon, we have here the image path and the captions. So of course, in the Flickr 8K dataset, it contains 5 captions for per image. So which is really good. Okay. So we can always have an options to how we can visualize those kinds of images. What would be the best captions for that? Unlike the other one that I actually showed you previously. So now let's try to, of course, show you how we can see it now. So just to give you an overview of how a certain image and then giving us the 5 captions. So from here, we have used a certain data from the Flickr 8K, and we actually show here at least the 5 captions. So a black dog is running after a white dog in the snow. And then the second one is a black dog chasing brown dog through snow. So that's and then 2 dogs chase each other across the snowy ground. And lastly, the last two dogs play each together in the snow. And the lastly is 2 dogs running through a low-lying body of water. So it's pretty interesting, right? Because we see a lot of different variations, which still in the same thought, right? But we just have those options. So now the next question here is that we have to now use the image feature extractor. Of course, on one images, it doesn't have that all those part of the bounding boxes needs to be put into words. It always think about what would be the most significant part of that image that would correlatedly or correlates to the output. So now, yeah, you will use an image model, pretrain, or ImageNet. So it can always be on that. Other kinds of models could also work as long as it's for trained for that ImageNet as well. If you can, so it extract the features from each image, and the model was trained as an image classifier. So we have to set it first into false because we wouldn't want to add the final classification layer at the end. So we'll just have that classification on the final for the feature maps. So we have to make it as false for now. So now our image size here is at 224 and 224. So it's pretty standard that we have to make sure that whenever we do use that, it's always that part right here. And another thing is that MobileNet is a very popular, transfer learning or pre-trained model, and then of course created by Google. So from here we can see that we are using the MobileNet VG Small for this one, and then we of course do some false here, and then we do some pre-processing, and then of course we wanted to fine tune our first. We want to unfreeze the layers on the last part, so we want to make sure it's false for now, so that we can fine tune it to another part. So that's basically how these things work for the image feature extractor. And then going to the next part right here is that we want to now, of course, resize it, our image for the model, because we don't want the big one. And so, yeah, so that's basically from here. So we're still using here the tf.io and then tf.image as well to resize it. Okay. And then going to here, we're just going to have our, the model returns a feature map. So this is going to be important part for our image captioning, because we wanted to see how this certain image or image captioning word works, rather than just running it and we don't see how this works. So now it generates different this, 124 and 3. Okay, so we at least we now see what we can expect from here. The next part, since we're done with resizing, we're done with the feature extractor, we're then seeing what kind of captions are we expecting in per image, or what kind of data sets. Now let's go with the next part, which is the tokenizer. So this is a very important thing, because again, we're using here the captions. So we have to now set that, okay, we want to have this kind of vocabulary for our captions. So here we try to transform the captions into an integer sequences using the text vectorization layer. So this is a very important thing, because again, the AI can only understand those integer sequences, right? So of course, the third point here is that to use the adapt to iterate over all captions, split the caption into words, and complete a vocabulary of the top words. So the top words is only the relevant part. We're not getting all the stuff and such. And second one here is that to tokenize all the caption by mapping each word to its index in the vocabulary, so that all output sequences will be padded to length 50. And then create a word to index and index to word mapping to display results. So since we're going to be showing some attention maps, or probably another one is the feature maps as well. So we have to have this part as well. It's very essential. Specifically, we're using the multimodal fusion as well. So now let's start to run this part. So this is just basically look at the words for the captions. And of course, in this part right here, since we wanted to tokenize it, so we just use the top 5,000 words for the vocabulary. And then we have used here the TF that cures that layers for text vectorization. And then of course we wanted to make it standardized and then send. And then now we have it for our caption data, right? So we expect that, okay, it's better much to visualize it later on. And then here we have this one, the tokenizer that adapt. So I'm gonna show you as these words later on. So here, yeah, we have this start and then end and on so on. So we're just taking out some words from the vocabulary that we actually set for. And now going here, let's have it part here. So we have this certain word, a cat and a hat, and a robot and dog. So it generates now the integer sequence that we're talking about. Okay, so we have to use that, because again, how does the model would actually learn or understand this without converting it an integer? And the next part here is a creating mapping for words to indices and indices to words. So this is very important, because we wanted to now see it later on whenever we train it. So we use a TF that cures the layers, and then of course a tokenizer, and then we're just calling it again the vocabulary that we actually have. And now we see this next part right here. So again, the bee, a cat, and hat, and so on. So these are the things that we mentioned for the tokenizer previously. And now let's have it prepared for our model. So let's run this. Okay. So for those are the following things. So let's just go over before we proceed to the modeling. Okay. So again, we first now show here the captions that we have. It's 5 per images. And then we did have here the image feature extractor, which is very important, because we wanted to unfreeze the last layer and try to use the feature map instead of you know and then we use the mobile net, the version 3 small, okay, because there's a lot of versions for the mobile net, but this one is pretty easy to use. And then of course it's trained on ImageNet, so if you're familiar with that, that'd be better. And then next year we try to resize it
according to our model, of course. And then here we see this 224 to 124 as well. And the next is to tokenize it, of course, since for our captions. And then now we have this 5,000 words, top 5,000 words for our vocabulary. And now it's ready for our, modeling. So now let's go here to prepare the data sets for the training. So here we have here, again, the image and the captions. That's what you see here. And then from here, it just repeats the cycle that we've shown here for the tokenizer, right? And then it returns the image and the captions. And now let's have this one part here. So let's show you this one. So this one is for the image caps, the path, and then the captions. Okay, so let's have the next part. All right, so this one, so to make sure that it's compatible with what they're gonna be doing, so we use this here, the Keras training dataset should contain the inputs and the labels, pairs. And for text generation, the tokens are both an input and the labels. That's something that we should take a note about. And this function will convert an image to text and pair it to an image input tokens and label tokens to pair. So going to next part here, well, this is pretty interesting because we're near to the how does it work now? Because we have everything started. So now we load the image and it grew images fail to load and then replicate images to match number of captions, shuffle so that we don't have anything like, and then rebatch the image and caption repairs. Then tokenize the text, shift the tokens, and add label tokens. Then convert the text from a rag tensor representation to padded tensor representation. So similar to how we actually do still the sentiment analysis, we still do tokenization, but just a little bit add on because we wanted to convert image to a text for the image captioning. Just a little bit difference on that. And then of course we just prepare the data sets. So we have here the batch size of 32, and then we wanted to shuffle it by 1000 and then load the image and make batches. So of course we use the tensor, we have the inputs and the labels, and then now we're going to be expecting, of course, the shuffled data sets that we have here for the training. And then here we have to install the feature extractor in your model and train on a data set like this. So I think we're pretty near on that part. So yeah, we have here the test for data and then train. And then going further, we have this. This is very optional for this one. So since the image feature extractor is not changing, so we're not going to use the image augmentation for this one. So we can either do this as part of it, but still it's an optional one. So we wanted to just save the dataset and load the dataset that we actually shuffled previously. So now we just basically load the image, just make batches, the same with how we did it previously. It's 32 per batches. And then we have this feature extractor, which we will run for each the batches. And then, of course, it's still up to us. It's pretty optional for this one. And then wrap the generated and the TF that data set. So this is what we're processing right now. And then, of course, apply tokenization, which is something that, of course, for the caption. Okay, so since we shuffle it by 1000, that's pretty started well. And then save the data into shared files. And then now load the data sets. So that's something that you could also try as well, but it's optional. No worries about that. And then, of course, we try to, okay, let me try to run this. I forgot to run this one. All right, okay, so let's just wait for a bit. It's just doing the mobile net and then basically for our train and test net, right? But so far, if you have any questions, just definitely ask for it.
Yeah, I guess we'll take few questions.
All right, let's see.
For the Pokemon one, there was one question like, are we fine tuning? If yes, how different is it from fine tuning LLMs?
Well, basically, when we say for this one, we're not using any large images, basically. So it's up to us if we wanted to build like an LLMs with more, better data sets, larger ones. So it's different how we fine tune it. But since on the Pokemon, I think it's around like 4,000 or less or more than that. But yeah, it's still different on how we fine tune it. But if you're asking for LLMs, maybe a different one to work on. Yeah, so that's something that we would probably explore. All right, so okay, let's go with the notebook that we're actually running so that I could Sure. There we. Oh, it's done. Okay. So now let's start with the training. Okay. So far we're already done with tokenization, all those stuff, and now let's make this ready. Okay. So of course, yeah, the datasets is all about the input, the label, and then we've used this keras as well, a part of it. And then the images has been already processed by the feature extractor model. And then of course we have this the input token. So the model looks at the text so far and tries to predict the next, which is line up the same location in the labels. So we have our input tokens, labels, and of course the images that we have here. So let's try to show you that. Okay, let's see. Okay, we have 32, 34 for the one, the label shape, and then this one. Okay, so let's get this ready on. Yeah, this is what we're expecting for that. And then now we're going to use the transformer decoder model. So now we assume that, of course, this is going to be more in the two-layer transformer decoder. It assumes that the pre-trained image encoder is sufficient and just focus on building the text decoder. So we're just assuming that it's just only the text that we're kind of focusing on. All right, so let's go with further here. So of course, to just explain this further. So here in the input side, the token embedding in positional encoding. So that's the sequential embedding. Next here is that the stack of transformer encoding. So this is mostly covered on this part. So let's try to now see it in some more part. Yeah. So let's go with next part here. So decoder is a standard transformer decoder. It contains a stack of decoder layers, which is very interesting to put on since we're trying to, create the captions for those images, where each contains 3 sublayers, a casual self-attention, a cross-attention, and feed-forward. This is actually very common, especially for transformers. And so we're trying to add this again for the layer for the casual self-attention. And then we have another one for the cross-attention layer, which will be going for our input images. And then again, for the feed-forward layers below. Yeah, so we're just going to run this again. And then next would be is arrange the 3 layers into larger decoder layers. So those are the 3, okay? And each decoder layer applies the 3 smaller layers in sequence. So after each sublayer, the shape out, sequence and batch sequence arrows. So that's how we actually look for the decoder. And then just gonna mix it all the 3. The casual self-attention, next is the cross-attention, and then the feed-forward. So of course, the output is we're just setting here all the layers that we wanted to have from the input, going to the layers, and then of course to the output. So at the minimum, the output layer needs to be in layers dense. So a general logic prediction for each token at each locations. And of course, we're just gonna try to run this one. Okay, so okay. Yeah. So another training for this. So far, this is I think it's faster than the other one. So yeah. Okay. All right. So it's done. So we have here the uniform entropy. So it will be helpful because the loss would be lesser, right? So this is very important whenever we train, transformer models. Make sure that their loss is reduced rather than it's increased. Okay. That's why we're having this one for the output layer. And then now build the model. So we already know that we have used feature extractor. We have here this tokenizer and then a lot of layers for the decoder layers and the output layers. So going here, just adding more for the caption. And then from here for defining all the caption or tokenizer and so on. So we're using the feature extractor for MobileNet. Again, the output layer. And then here, dropout rate. So we need to have that as well as part of it. And then since I mentioned that we're just using the 2 decode layer, so we're just having this 2, okay? And same with the num heads as well. So now this is the best part. We're just gonna try to see which one this kind of works, right? Okay, so let's have this ready. Okay, so yeah, it's all, yeah, this one. So blue cat after red busy of his pool of a block back as well. So this is really, it doesn't make sense yet, but once we have an image that we're using, so let's try to start it. So of course we have again the usual for the training, we have the loss and matrix, the optimizer, and of course the callbacks, which is actually optional for this one. But I would suggest to have it as part of their image captioning. And so for the losses in the matrix, just the typical, model we create. So we have to see the losses in the matrix, but the metrics for this. So we're just gonna have this as part of it, and then the callbacks so that we can generate some captions for the surfer images at the end of each epoch. So which means that, for example, we're training again now in each epochs. So we're gonna be expecting that there should be a caption per epochs. So that's why we're using the callbacks for this. Okay. And of course, it generates the three output strings. So that's one. And then like before, the first is greedy, and then the other one goes next. So I think for this one, we have to use a callback so that we can see, okay, is this working and not. Right. So that's what callbacks. And now let's go with this. All right. So now that we're already done with the compiler of our model, so let's see how this gonna works on the ebook. It's actually fast, like compared to the usual training of the image captioning. For this one, it's just gonna be as fast as we can. But yeah, let's just look at that. So all right, so just maybe we can accommodate questions online if we have someone here.
Okay. So we'll take another question.
Okay.
Can you please tell the dataset name of the Pokemon? So I just replied saying that it is Pokemon Blip. So I hope that's correct, right?
Yeah, it's Pokemon. Yep.
Okay. So this is the dataset name, Pokemon Blip captions, and you can check it out on Hugging Face. So we'll take the next question. Like, how do you evaluate an image caption model? Is there a bias variance analysis designed for it to know whether the model is overfitting or underfitting? Thank you.
Well, this is actually very interesting. Well, actually, gonna show you later on since we're starting to train this one, but maybe we could show it later. Yeah, I think it's almost done. Yeah, so maybe we could later on show that as well. So basically, from here, I'm just gonna show you. Maybe we can answer it later on. But from here, since I mentioned we use the callbacks, so now whenever we do the epochs, after the epochs, we have this three, of course, captions. We have this, a man in a red water, a man is on the white on the dog, and then and so on. So why do we have to do that? So that we can show which how this works. But a little bit of context from here, it's not, well, whenever we build other, models, it takes a lot of time to train. Sometimes that's one of the challenges that we always think about. But for this one, since we're using image captioning, it's pretty much, it just gonna takes a little bit, minutes, but not like an hour to train this. So like for example, here we're like already in the 12 side. So I'm just gonna show you later on the one I actually showed you, this one. Let me try to go further here, like this one. So maybe we could later on show this part. But going further while we're waiting for the training, so basically from here we actually use this another one, the efficient B0 model. So since in previous ones we use the MobileNet and the other transformers for the Pokemon. So this one is also a family of the CNNs, which is built by Google. So which you can actually now see that it's for improving and scaling the models compared to just basically running the model, and then sometimes the accuracy is not still as high as we can see. So DCNs not only provide better accuracy but also improve the efficiency of the models. That's why it's named EfficientNet. So that it reduces the number of parameters as compared to the other state of the models. But basically this is the baseline, the BO. But there's another B1 up to the B4, I think. And then we have here this one, architecture. So this is what I could see from how we put into starting from the input image and then going further to the convolutions, to the MB convolutions, and to the other block 5, 1, 2, actually 7. So before it generates the feature map. And so the building block of this architecture is the mobile inverted bottleneck, which is also helpful for the efficient, especially it is the baseline. So it's pretty much more comprehensive when you look at to the further other models of EfficientNet, like the B1 and the other one. The parameter is getting really reduced. And then we have here this EfficientNet is a mobile friendly pure convolutional model. So that possess a new scaling method that uniformly scales all dimension and the depth with resolution using a simple yet highly effective compound coefficient. So this is actually the baseline. So the reason why it's because sometimes whenever we train certain transfer learning model, and like for this one, for this data set, it takes so much layers. You have to increase this and look at the further one. So that's the one you're seeing as well for this. So let's check the notebook we're training for, how it's doing so far. Let's look at it. Okay, it's 32. So maybe we could entertain more questions so that we can show you later on, um, or any. So far, are you guys getting the image captioning? So we're showing two different models simultaneously. Hope that you're not confused on this. Yeah. But actually, there's one thing that I also wanted to. Yeah, sure. Do you have a
Yeah,
question?
sure. Go ahead.
Yeah, got it. So there's actually one thing that I could also think about. Since we actually showed the Pokemon previously, maybe you could also try other images that you think that would be pretty interesting. Like if you're into gaming or other stuff that related to how we could generate captions, probably you can explore more of that and try different kinds of transformers aside from what we actually showed to you, and then also use other kinds of this. So it's pretty much how you're gonna make this more creative, but at least the kind of data set we're working on is pretty diverse, since Hugging Face has this open source data sets that you can work on, and pre-trained models are pretty easy to start off. Basically, the first model um has more fewer lines compared to the one that I was showing you, this one, but it's pretty more direct. At some ways we can really get more info to this. So yeah, that's one thing. But and yeah, let's look at to this. So basically, this one we can see the loss. Well, it's not really that high. Well, that's a good thing. It's not really that high so far. And then we have here, yeah, the loss and mass accuracy. So pretty much we can see it later on. How was it? Okay, so let's see. All right, so we're almost getting done. Okay, so I'm one in a red t-shirt surfing, and then other one. So perhaps let's accommodate more questions from our audience. What do you think, Tarun?
Uh, I guess the previous question was related to the evaluation itself, and one more was this one. Sorry. May I ask if it is free to access GingFace APIs? Thank you.
Oh yeah, that's basically an interesting question. Actually, when you create your account in Hugging Face, it will actually direct you in this part. So when you click this access tokens, you're just gonna be copy pasting it and just put it on your notebook if you just wanted to access it for the data sets, the models that you're gonna be using. Pretty much on this, but let you show you this one probably for a reference for the metrics. So on the Pokemon lead, so we use this what we call word error rate. So it's different to how we usually assess the performance of the models. So it's common metric for performance of automatic speech recognition system. So this is actually available also on Hugging Face. So one pretty interesting about Hugging Face is all of the stuff, metrics, all the information of a certain model is there, and even some of the stuff that you need for when you're starting on building, generative AI, models. And sometimes, yeah, here that it's hard to actually see the performance of the words. Sometimes it's pretty complicated than how we use it on some numbers and so on. So from here, the word is derived from Livingston distance, working at the word level instead of phenom. So maybe you can check this one. And the word is available to for comparing different system as well as for evaluating improvement within one system. So it's actually computed by this one. So which actually shows that the S is the number of substitutions, D is the number of deletions, I is the number of insertions, and other things. So this is basically useful whenever we also work into some like image captioning. So this is one way to think about that. And then probably we can have this as well. Okay, so maybe we could show you the metrics for. So metric card for word. So word error rate is a common metric for the performance. That's it. And then we're just having this formula to compute that. So I'm not sure if you're familiar with the perplexity. We can usually use it for clustering some of those models. It actually helps determine how the clusters were performing, but just a little bit different from this one. And then another here is that we can now evaluate how it works. So this metric output representing the word error rate. So the lower the value, the better the performance of the ASR system, with the where of being 0 as the perfect score. So I hope that answers actually your question, especially for this case of image captioning. You can actually look into the where, and then of course we have to check how reliable the model that we've actually done by using the word score. So this one, since it's 0.5, it's pretty much close, but like still we hope to have less or more word scores so we can have it at least. And so yeah, some papers needed this, and then example. So from here it's perfect. Well, pretty much perfect one because it's 0 0.0. So for example here we import the evaluate, and then we added the where for metric, and then we use some predictions here in hello world, good night, moo, and the references, hello world. So it's pretty close actually. Looking at this, it would eventually have a 0 0.0 because again, predictions and reference is pretty close to each other. No differences, so that's why 0 0.0. And then another one here, just look at here, the partial match. So for example, we have this predictions of, this is the prediction, there is another sample. And the references we're looking into is that this is the reference, there is another one. So pretty like there's still a difference because again, another here, and this one another. So it's, well, it gives us a 0.5 word score, which is still partial match, but not like very closest to perfect. And then if we can say now it's if it's doesn't match each other, no match. So when we say here like hello world, good night moon, and then the other one is hi everyone. Well, 1.0 is it just means that it doesn't match with the references. So I hope that makes sense for the metric scoring. So for example, the captions that we predicted and then the references, if it's closer to that, then the worst score will actually eventually look at either partial match, no match, or it's perfect. And then we have here the limitation bias. So of course, this is one thing that we need to also measure as part of. That's why we're showing this as part of this metric. So hope that actually answers your question. Or yeah, okay. So any questions from our end?
Uh, we have one question like, how are CNN image feature passed to language models? So this is in the context of image captioning.
Okay. All right. So this is very interesting. I think I mentioned this a while ago. Maybe okay. How are CNN image feature passed to language model? So okay, let's go up and just show you this one. So again, I've mentioned two things, the image feature extractor, and then we have for the other one, which is for the tokenizer for the word. So again, we're thinking about, we have an image and we have these captions. So we're combining this both to actually work on that image captioning. So for example, here for the image feature extractor, we want to now, just treat first the model, and then we hope to have the feature maps after that part as well, once we now give this layers. And then for the captions, we wanted to highlight here this tokenization so that we able to put that words into an integer sequence. So combining that both would actually work into the model we would have here. So let me maybe just show you the model we're having this. So it's pretty great question actually. So this is where we now have this transformer decoder model, which very sufficient to having, let's say, an image and then a caption works on both, right? It's so basically from here we have set this kind of layers. We have the input image, and then basically just have this all these layers added, the cross attention, then the feed forward, and the other one, and then later on we have this outputs as part of it. So basically it's combined on the side of, since we're using the mobile net, and then from here we define some part of the caption. So it doesn't really directly to saying that it's different two models we're using, but basically they're combined together, and um that's how it thinks of looking at this. Maybe we can also helpful this for this one. So we have here the tokenizer as part for the captions, and we have this feature extractor for our images. We use the mobile net. So that's how things works for this one. Okay, hope that that actually answers your questions. Okay, let's check our training here if it's done. Hopefully it's done. Okay, I think it stops probably in my. All right, so okay, well, maybe I just give you again this one. So I since I mentioned already the stuff that the flow we've done and we've used here. So we just basically look up to the output here. This is gonna be the output. Also, we're gonna be using for this. So let me try to show you this. So of course, at the end of the training here, we want to see collectively how the captions are working per bounding boxes. So here we have this entire from the start to the end, which I actually showed you a while ago for that notebook. And then we have there a man in a red a shirt is surfing and end. So we have the starting and the end. Then each of these images and then bounding boxes, it defines a certain word. And if we try it to another trade model, to new images, it's actually the same one we're gonna be showing on later. If yeah, but basically this one works on another one case. So the I think a man is sitting on the bed. So from here, so a man sits on a bed. So looking at that, it just traces some of the relevant features based on the feature extractor. And then now we can get this attention maps that we're seeing here. And then here we see on a bed with a white and a white dog and so on. But it does make sense because still it needs more improvement. It's not perfect, but still it can be improved later on once we, train with more with data sets or probably explore into different kinds of models. And then here, of course, for the more captioning results on the previous for the Pokemon, well, this one will eventually will also show us that some of these generated results still has like something to improve on. For example, the second one, a drawing of a Pokemon character with RE. So it's still incomplete, but still we see some very good results on the other side. So a very cute looking character with big eyes, and then other ones and so on. But it's pretty nice that we can see that it uses certain words that actually give description to that image, although it's still not as very complete as we can, but still a good part. We can see that we can generate still an image from here. So same with the other one here. So Carter, red Carter laying on the ground. Well, it's really nice that okay, but it doesn't show any like an octopus or something. So it still needs more. Probably the vocabulary needs more than 5,000 could be that. And then a cartoon character holding onto a pole. Well, it really makes sense. And same with the other one here. The last one here, it's very interesting. A drawing of a Pokemon with a blue hat. So, well, it recognizes that it's a hat, right? So basically, that's how the image captioning works. So hopefully, for this one, we were able to actually share more those two. So hopefully, we're not overwhelmed of the using of two different models and two different data sets. So I think that's pretty much Karen. Yeah, we can probably have yeah.
All right. So, do we have any questions? Okay, so this one was the previous one, and
Yeah.
okay, so we'll wait for 2 minutes until we have few more questions. And once again, thank you for accepting the invitation. And I just saw that you already came back from Keras Community Days, Manila. As I'm a TensorFlow User Group Bangalore organizer, I was aware of that today was Keras Community Days. I
Yeah,
hope that
yeah.
went well. And completing that and talking at this event, I appreciate the hard work. And yeah,
Yeah, thank you so much for the invitation. Really, really to actually speak here. Yeah, I think we don't have any questions so far. Everyone is maybe they've done it before.
Okay, so I'll just add the Discord server channel invite so that if you have any queries or discussion, you can make sure you join this chat and ask the questions related to LLM Bootcamp or also multimodals in particular. And if you have any queries regarding the notebooks, what are shared, and you can ask those questions in Discord, and we'll try our best to answer those questions. And I'll reach back to you if there are queries that I can't answer. So, yeah, once again, thank you. And if you have any closing thoughts before we end this session, you can go ahead.
Yeah, I think for those who are starting out in generative AI, I hope they could explore different models, not just one. Especially now that every day there's like new models coming in, so it's pretty much overwhelming for starters. But definitely just continue exploring, not just in the image captioning, but the rest of the bootcamp sessions that will be discussed later on. So yeah, thank you so much for joining with us.
Yeah, and I have one closing thoughts like as Armielyn mentioned that you need to explore different models. In this context as well, related to multi-models, we have added an example of OpenAI clip, which uses vision transformers and like this particular notebook which we have uploaded on the content page, it takes the image and we take few random text, 5 to 6 text, and based on the probability score of the caption, it tells which is the accurate caption to that particular image. So you can work around with this and play around. It's really very interesting model that was built by OpenAI. And these are my closing thoughts related to multimodal models. It's really very fun when you explore. Obviously, it takes too much of time to train the model because we have images, and all these images are more than 500. We have more than 500 images, and in order to extract all the feature, then pass it to the language model, it takes time. So once you are able to train, the evaluation is something which you need to play around. So yeah, I hope you have fun with multimodals, and we'll see you back in LangChain on how you can build a chatbot that can chat with your own PDF and extract few of the context, and then you can make this particular bot as ChatGPT using LangChain. So this will be on the next week, September 16th, and then we have Llama Index, getting started with Llama Index and few of the components to get started with chatting with your own data. We have multiple. You have multiple components like memory, then you have a prompt template, parser, and as well as you have chatbots, different chat models. So yeah, so we have one last question. What is the specs of the computer to be able to keep with CNN?
Yeah, I think this is pretty interesting question. But if you're using Coca-Cola or probably Kaggle notebook, you don't think about the GPU. But if you wanted to run it locally, well expect that your RAM would eventually go and heat up. So maybe you can use those Coca-Cola and other notebooks that cloud-based, especially the Kaggle. I think Hugging Face already have this, right? The environment to train the models. So probably you can explore those are three things. Yeah. Yeah, I think you're muted, Turin.
Oh, sorry. So I was just telling that thank you for joining today, and we'll see you in next session. Thank you, guys.